So, we are going to extend the discussion on oblique shock to something called shock reflections. Okay. So, it is going to be reflections or shock interactions, shock interactions. Okay. So, what do I mean by shock reflection? So, suppose I have a plate here and I have a flow which is greater than 1, and somehow I have a oblique shock here. This may be due to a body that is kept here at some angle, or due to whatever. Let us forget about the reasons why we have a shock here, we just have a shock here. So, there is a shock here. So, as we know, there is be a velocity vector that is coming, streamlines that is coming. Because of the shock, there will be a turn. Now, somehow the flow after this, if this is an infinitely long plate, the flow somewhere has to turn towards the in line with your surface. So, if there is a flow that is at an angle, this goes and hits the surface. So, to avoid that kind of scenarios, the flow would take another shock wave, which is the reflected shock wave from the surface. So, the flow comes here and makes a turn like this, so that the streamlines are in parallel with this thing. Now, this happens because we are doing a inviscid flow analysis, we avoid separations here. So, in reality there may be a region where you can have a shock that is going like this within the boundary layer, and it can reflect like this. So, there will be region here which can have separations which are typically due to the shock, typically called as shock induced separations. So, you can have oblique shock that is going to take you this way, or you can have streamlines that is going this way within the boundary layer. You can also, if you consider viscosity, you can also have separations and other things. Let us not discuss that, rather we will discuss the first case, which is the inviscid flow, and we will restrict to a flow like which is a regular reflection from the surface. Okay. So, I have a reflection from the wall and then I get it. Or if I can have, if I have a channel which suddenly reduces in area. So, if I have a channel like this, so the Mach number, incoming Mach number is greater than 1. So, because of this there will be a oblique shock that is formed here, and because of this top surface there will be another oblique shock that forms here. This can interact at some position. If these angles are same, they will interact at the center line. Otherwise, there would be a different location in which they interact depending on this angle, say alpha 1, and this angle alpha 2. Okay. And once this reflects, there will be another oblique shock that is formed out of this. Again, the flow direction you can get it. So, if you know these angles, if you know the deflection angle from our theta beta relation, you can further get the angles at which the outcoming flow is. So, you can have m1 greater than 1 here, and then you have a region here. So, this is region 1, this is region 2, this is region 3, and this is, so I call this as region 4 and region 4 dash. Okay. So, depending on if these angles are same, then I can have 4 and 4 dash of same kind. Otherwise, the Mach numbers here at 4 and Mach number here at 4 dash can be different depending on the angle at which these shocks are reflected. Okay. So, we are going to do some problems related to this. So, all this because a uniform constant area duct suddenly deflects at 2 different angles, and there are shock reflections that is happening here, and the streamlines are going to do these kinds of phenomena. Now, the point to note here is that I have drawn a dashed line here. Okay. So, this is a region where demarcates 4 and 4 dash. The 4 and 4 dash, the properties in 4 and 4 dash, namely the Mach number or the pressure or entropy change, everything depends on the angle at which these shocks are reflected within 4 and in 3 and 2. So, if the angles are same, 4 and 4 dash should be same, otherwise the entropy change across these, the top shocks are different from the bottom shocks. Okay. So, there is a sudden entropy change, that entropy change at 4 and the entropy change in the region 4 dash is different. So, there will be a discontinuity of entropy change in 4 and 4 dash, and that happens at this particular dash line, which is called as slip line, where my entropy change is discontinuous, my Mach number is discontinuous, except the pressure P4 is same as P4 dash across the slip line, and the direction of velocity. Direction of velocity is same across slip line. Okay. All other properties can have a sudden jump, temperature can have a sudden jump, or all those quantities, densities can have a sudden jump, everything can have a sudden jump. So, if you take a pressure contour of this, you are not going to visualize the slip line, whereas if you plot the Mach number contours, you will see a slip line according to this particular configuration. Okay. Now, same thing is happening at a flow in a nozzle. So, if I have a CD nozzle, okay, if my PB is between PB critical 2 and PB critical 3, which means my shock is, so if I have a isentropic solution like this, so this is my PB critical 3 and this is PB critical 1. Now, if my shock is outside the nozzle, so which is if I have a shock here, I have a PB critical 2. So, if my back pressure is between these two values, I would have a shock that is happening outside the nozzle. Okay. So, in that scenario also you would see these kinds of flow, the schematic of which is what I have it here. So, in the slide what you have here is the PB critical 2, which is Mach number, some Mach number where the shock is sitting at the exit of the nozzle. Now, if I reduce my PB further, this shock is pushed downstream, and hence you would see a oblique shock, a strong oblique shock sitting outside the nozzle. Okay. And your Mach number after the shock is typically less than 1. But if you reduce, keep reducing the pressure ratio is PB by P0, then I have a reflection shock like something like this. Okay. So, your shock is pushed further down. So, you have shock reflection, and this is this straight normal shock kind of thing is called the Mach reflection, because this normal shock reflects with the interact with the oblique shock here. So, this kind of shock interactions are also possible, and we are going to analyze a few of these kind of these green lines are called expansion fans, which we will deal it in the next week lecture. Okay. So, we will try to do. So, this is a over expanded nozzle, what this scenario is. So, when it goes further down, if the back pressure is further down than lower than PB critical 3, you will have the under expansion. So, this over expansion happens here, and this phenomena what we have drawn here happens in an over expanded nozzle. Okay. So, what we will do is we will try to evaluate, we will do a numerical problem to see what happens further with this kind of analysis.